Hello everyone. In this note set, we are going to be talking about chemical formulas, molar conversions, empirical and molecular formula. So, to just start out, let's define a couple of different versions of chemical formulas that you could see or deal with. First of all, when you're writing a chemical formula, the purpose of it is to be a quick abbreviation that's going to tell you what atoms or elements are in that compound, and also how many of each are in that compound. So if you were not already aware, a subscript is going to represent specifically how many of each atom are in that compound. So if I were to write glucose out, C6H12O6, the 6's and the 12 are going to tell you, well, how many carbons, how many hydrogens, how many oxygens are there. However, if you have an exponent attached to a chemical formula, like say we've seen before with our polyatomics, SO4 2 minus, don't know why I put a plus there, it's minus, or even NH4 plus, or even our single elements, if we have a bromine with a minus charge, any of that is going to represent a charge specifically. So when you are writing out a chemical formula, if you are writing that out for a neutral molecule, a neutral compound, you shouldn't be including an exponent. But if you're writing a formula for something that is not neutral, like our polyatomics, like our atoms in ionic state, you need to include that charge as an exponent. All right? An empirical formula is a simple or reduced whole number ratio of the atoms in any particular compound. So we can look over here for a decent example of an empirical formula. We have this over here, which is C2H5, which just basically means that in any molecule that fits this empirical formula, for every 2 carbons, there will be 5 hydrogens. But that can be scaled up into a molecular formula, which is going to tell you the actual whole number ratio of atoms in a specific molecule. So in this molecular formula that we can see on the right over here, we see C4H10. We can reduce that to C2H5, right? Because it's the same ratio as the empirical formula. But in this particular molecule, there are actually 4 carbons and 10 hydrogens. So let me give you a really quick example. With the glucose molecule up here that I referenced, if I were to write glucose's empirical formula, I would be writing C1H2O1, right? Because there are double the amount of hydrogens in this glucose molecule than there are carbons or oxygens. But its molecular formula is C6H12O6 because there are actually 6 carbons, 12 hydrogens, and 6 oxygens. Okay? Other 2 formulas you should be aware of are something called a condensed formula and a structural formula. So structural formulas are just written out so that you can see the structure, right? Anytime in regular chemistry when I asked you to draw a Lewis structure, that was a structural formula. A condensed formula is something that we hadn't really dealt with very much in regular chemistry. But it's just a slightly expanded version of this one, but it's drawn out in such a way so that you can kind of see the orientation of different functional groups on that molecule. So you know that one end is going to be a CH3. There are some CH2 groups in the middle and a CH3 group on the other end. So let me use a different color to kind of point out to you the different parts of the structural formula that correspond to the condensed formula. This CH3 group on the end over here is represented here. We have a CH2 group in the middle, CH2. We have another one right here, CH2. And then on the other end, we have another CH3. So you can kind of see how a condensed formula would be a little bit more representative of what the molecule actually looks like structure-wise, but we're still not drawing out the whole entire structure. So you might see that going forward. The only times we really dealt with it in regular chem were when you saw acetic acid. You could see it represented a couple of ways, and a few of you would ask me questions when that came up at that point. Moving on to calculating the amount of moles in molar mass. So first of all, what is a mole? It is also known as Avogadro's number, specifically 6.02 times 10 to the 23rd power. It's a really, really big number. But all it is the standard international unit for amount of a substance, right? Because we all know what a dozen means. We know that 1 dozen equals 12, right? 1 mole is that many. It's just an amount that we've come up with. And it's the objects specifically in a fixed mass of a substance. The number was calculated using carbon way back when by Avogadro, doing a lot of experimentation and a lot of calculations. But basically, he figured out that in 1 mole of carbon, there were that many carbon atoms. So with that, we can extrapolate to mean that 1 mole of any substance has that many atoms, or 1 mole of water has that many molecules in it. So this bit you can scale up. It doesn't necessarily have to mean atoms. It could mean particles, or it could mean molecules, or it could mean textbooks. If you have a mole of something, there's that many of it. This bit of information is going to become very important later. We can say that I have 1 mole of water molecules, right? And that would mean that I have 6.02 times 10 to the 23rd water molecules. But if we look within that molecule, if we were to break that molecule up into its base parts, its hydrogens and its oxygen, that would mean that in 1 mole of water molecules, I have 2 moles of hydrogen because of that little 2 right there. And I have 1 mole of oxygen because of the invisible little 1 that we do not have to write. And that ratio is never going to change as long as I am still looking at water. All right, so moving on to our cool periodic table square down here, we already know a little bit about it. We already know that this top number is going to be our atomic number, representing our amount of protons and our amount of electrons in neutral state. The bottom number we have defined so far as average atomic mass. And the unit that I gave you for that was atomic mass units, AMU, right? However, this number is also how much 1 mole of that substance weighs in grams. So it's also a molar mass. And the unit for that is going to be grams per mole. All right, so once again, if I ever ask you to find the molar mass of any particular atom, you are going to look at the bottom number on every square of the periodic table. Even if it's the molar mass of a compound, you're going to look there to add up some different molar masses of different atoms to make up that compound's molar mass. All right. Next thing we have to talk about is the molar conversion chart. Our molar conversion chart is used specifically to convert between moles, mass, and particles of a single substance. This is one of the biggest mistakes that I see in regular chemistry. People start confusing the molar conversion chart with stoichiometry, and this is not stoichiometry. I know it's not stoichiometry specifically because all of these conversions are going to be done about a single substance. When you're doing stoichiometry, that chart is going to be a lot bigger and a lot more complex looking, but B, the most important key is that you need a reaction for stoichiometry specifically. And you need a reaction because you are actually converting between different substances present in a reaction. So once again, if you are trying to convert between moles, mass, and particles of one substance, you are just using this molar conversion chart right here. Now, it looks a little bit complex, so let's walk our way through it a little bit. We have moles in the center, And from there, we can convert to a lot of different things. If I want to go between moles and particles, I'm going to use Avogadro's number. I'm either going to be dividing or multiplying to get back and forth between moles and particles, because we know that 1 mole is 6.02 times 10 to the 23rd things. Again, could be atoms, could be particles, could be molecules, it could be textbooks, literally whatever. But if you have 1 mole, it's going to be that many. If I wanted to go between moles and mass, then I'm going to use these little equivalents over here. I'm either dividing or multiplying by a substance's molar mass. And just so you're aware, molar mass, you need to find that, and that can be found on the periodic table. All right? If I want to go back and forth between moles and solution volume, I'm going to need that substance's molarity. And molarity is a concentration. It is expressed in the amount of moles divided by the amount of liters that you have, and we will get to solution concentrations and how to use them. I'm not going to focus on it too hard right now. Last but not least, if you wanted to go back and forth between moles and a gas's volume, you're going to use this equivalency right here, that 1 mole is equal to 22.4 liters of a gas, specifically at STP. So let me explain STP real quick. That stands for standard temperature and pressure. Specifically, there are 2 values. To be at standard temperature and pressure, that means 1 atmosphere of pressure and also 273 Kelvin. Another way to say 273 Kelvin is 0 degrees Celsius, because that's the same thing. We can convert back and forth between Celsius and Kelvin. But I'm going to be honest with you, most experimentation does not happen at 0 degrees Celsius. It does not happen in a freezing room. Instead, most experimentation is going to take place in something called standard state, and standard state's a little different. That is going to be roughly 1 atmosphere of pressure still, but it's going to be at 298 Kelvin. And it occurs at 298 Kelvin because that's about 25 degrees Celsius, which is roughly room temperature. There's a little bit of variation there, but it's considered 298 Kelvin as standard state. So for our calculations, if you are using gas volume, if you're using this molar conversion chart to go into a gas volume, we are going to assume, unless we are told differently, that our cool experiment is happening at STP, specifically so that we can use that equivalency. All right, so let's move on into actually learning how to use this in practice. All right, how to use the molar conversion chart. My example for you is pretty simple. 1 iron atom has a mass of 55.85 AMU, and 1 mole of iron has a mass of 55.85 grams. So, therefore, we can assume, based on Avogadro's countless calculations, that 55.85 grams of iron is going to contain 1 mole of atoms. Okay, and all that information is coming from the periodic table in terms of its molar mass. So our practice problem, wherein we are going to practice using this chart, is how many atoms are contained in a sample of carbon that weighs 15.34 grams. And we're going to do this using a simple conversion. We always want to start with our given number. Let me zoom in a little bit. Our given number is 15.34 grams, and I'm also going to put carbon there. All right, I want to know how many atoms are contained in that sample. So what do I have? I have grams. Grams is a mass unit. So I'm going to start here on the mass side. I want to know how many atoms are contained in that. So I'm going to go to the right here. I'm going to go towards moles because the way to get to atoms is on the other side over here, right? So I know that 1 mole of carbon on the periodic table weighs 12.01 grams. Okay? But I'm not done yet. I've made it to moles now because that is the unit in the upper corner of my little conversion. So I'm going to add a second step. Now I'm going to follow this right arrow again, and I know that 1 mole of anything is 6.02 times 10 to the 23rd atoms. All right, so now all I need to do is I need to pull out my calculator and do that calculation. You should do it with me just so you have practice plugging in complex numbers into your calculators. All right, so what I get at the very end is 7.689 times 10 to the 23rd atoms. All right, so real quick, we're going to do a little bit of analysis to see if that number makes any sense. First of all, what I know based on the periodic table is that 1 mole weighs 12.01 grams. So just looking at my given number up here, I know already that I have more than 1 mole of that substance because 15.34 is more than 1 mole of carbon weighs. So if I also know that 1 mole of anything is 6.02 times 10 to the 23rd atoms, then my answer should be greater than that value because I have more than 1 of my substance. And indeed, I find that 7.689 times 10 to the 23rd is greater than 6.02 times 10 to the 23rd. So it is highly likely that this calculation is correct because my answer makes sense. Okay. So I'll just take a second to erase all of this stuff and we can do the second practice problem. Now would be a really great time for you all to pause what you're doing and try this problem on your own. However, if you're not really comfortable with the conversion yet and you would like me to explain it to you, I'm going to explain it anyway, so you're welcome to keep watching if you want. Our second practice problem states, a sample of gaseous nitrogen has 6.7 times 10 to the 24th molecules. So that's my given number, and I'm going to write it down. I'm just going to abbreviate molecules. What I want to know is how many liters is that sample going to be. So let's take a look at the conversion chart and let's see where we need to go. I have a lot of molecules, so I'm going to start over here on the particles side. And what I want is liters, and it's gaseous nitrogen, so I'm actually going to be going that way. So what I'm going to do is I'm going to go follow this left arrow and then follow that down arrow. All right? I know, since I'm starting at particles or molecules, that 1 mole of anything is 6.02 times 10 to the 23rd of that thing. In this case, it is molecules. All right, so that is going to take me here to my middle step, moles. I also know that at STP, which I told you we were assuming things were happening at, unless we were told differently, that 1 mole of that thing is going to be 22.4 liters. All right, so now all I have to do is finish out my calculation. I do my 6.7 times 10 to the 24th times 1 times 22.4, all divided by 6.02 times 10 to the 23rd times 1 on the bottom. At the very end, I end up with 249.3 liters. But we have to ask ourselves, hey, am I using the correct amount of significant figures? So we got to look at our number in our problem. 6.7 has 2 sig figs, so I'm actually going to end up rounding this answer off to 250 liters because 250 has 2 significant figures. Okay? So that is simple molar conversions. However, it's not always one atom or one element that we're going to be doing molar conversions for. Sometimes it's a compound, sometimes it's something a little bit more complicated. So let's just go over real quick how to find molar mass if I'm going to do a conversion with a compound. All right. Molar mass, once again, is defined as the mass per mole of its entities with units of grams per mole. So how much does that thing weigh on the periodic table, pretty much? All I have to do to find molar mass for any particular substance is just add up whatever's in that compound, right? So if we look at sodium oxide over here, we notice that there are 2 sodiums and that there is 1 oxygen. So I'm going to add up the molar mass found on the periodic table for sodium, and I'm going to add it in 2 times because there's 2 of them. And then I'm going to add that with my oxygen to get 61.98 as a total molar mass. So once again, simple addition, very, very easy. All right, couple of practice problems just because. This practice problem states how many moles of calcium phosphate are in 43.67 grams of that compound. So before we do anything else, before we start setting up a conversion, we know that we are going to have to figure out the molar mass of this particular compound. So let's do that real quick. I know that there are 3 calciums. So I'm going to take 3 times the molar mass of calcium, which on our periodic table is 40.08. I'm going to have 2 phosphoruses. This 2 on the outside of that set of parentheses is going to distribute to both of those things, right? So I know that I'm going to add phosphorus's molar mass twice, and that's going to be 30.97. Last but not least, we have our oxygens, and we actually have 8 oxygens here. 4 times 2 is going to give me 8, so I'm going to have to add that 16 8 times. And if we break out our calculator and do that on a calculator, we get a full molar mass of 310.18 grams per mole. I know it's grams per mole specifically because I told you that that was the unit for molar mass. All right, next, we've done that, so now we can actually do our conversion, right? This is my given number, 43.67 grams of calcium phosphate. Yes, I am putting in that full chemical into my conversion chart. You should too. And let's take a look at what we're going to do. I'm starting with a mass in grams. I'm going to follow this right arrow towards moles. So I know that 1 mole of calcium phosphate, I just figured out that number, is 310.18 grams. Now, please note that this unit got split up when I was using it in my dimensional analysis. That mole went on top. Since I'm dividing by grams per mole, the mole actually moves to the numerator. When I do that calculation on my calculator, I am going to get an answer of 0.1408 moles. I'm using 4 sig figs because my original number here had 4 sig figs. Let's take a second to make sure our answer makes sense. We know that 1 mole of this substance is 310.18 grams. I have substantially less than that to start with, so it makes sense that I'm ending up with a small amount of moles at the end. Okay, one more practice problem. Once again, now's a great time to pause the video and try it on your own, but if you'd rather not do that, you can listen to me explain it as well. We're starting with ethanol, C2H5OH. We can also write that C2H6O because that's just going to make it a little easier to total our elements. So once again, you're seeing a difference between a formula that's written out to identify that functional group on the end versus our plain molecular formula over here. So just to point out that difference. In this molecule, we have 2 carbons. Each carbon weighs 12.01. We have 6 total hydrogens. Each hydrogen is going to be 1.008. And we have 1 oxygen, which is 16. Add all those up, we get a final molar mass of ethanol that is 46.068 grams per mole. Just to consult our conversion chart real quick, once again, we're starting with a gram amount, and once again, we are going to the right towards moles because that's what the problem asked us to do. I'm going to put my given number, 33.64 grams over here, and I'm going to put my formula as well, C2H6O. I know that 1 mole of that thing is that number, 46.068 grams, and I can plug that into my calculator to get 0.7302 moles. My answer once again makes sense because my given number was less than 1 mole of that substance, so it makes sense that my answer is less than 1 mole. I will continue on with these notes in a separate video, but hopefully that wasn't too hard for you. Please ask me if you have questions.